Hey guys, so it's been a little while since we had a video. Actually, that's not true. That's not true at all. Either way, so now we are talking about a concept known as the mole concept. And so remember in the beginning of the year, in October, I dressed up as a mole, and you guys didn't understand why. Well, now we're going to learn about the mole and why it is important in chemistry. So I want you to think back to when we did dimensional analysis at the beginning of the year, because now it's coming back, and I told you guys we would use this throughout the year, but now we're going to focus on converting. And so in order to do that, you need to be able to use dimensional analysis. And remember, that's canceling out different units to get to something else. So for example, if I said how many days are in a year, and you had to show me that with dimensional analysis, you would do a conversion factor. And so again, I am going to review this in class. So if you're super confused right now, if you're super worried, don't stress yet. By the end of this video, you should be able to identify 3 methods for measuring the amount of matter in a sample, be able to define the mole and its relationship to Avogadro's number, use Avogadro's number to convert between moles and the number of representative particles of a substance, relate the atomic mass of an element to its molar mass, and finally calculate the molar mass of a given compound. So I want you to take a minute and think about the last time you baked anything or you cooked anything or any time that you added something to be a precise number. And you did this because you wanted a specific outcome. So for example, if you're baking cookies and you put too much flour, let's say you dump the entire bag of flour into your cookie dough, you're probably not going to get very good cookies, and they're probably going to be too stiff. They're probably not going to taste very good. So it's really important to use measurements in order to accurately get what you want. And so I want you to think of chemistry in that way. So yes, we can make an explosion by pouring this into this, but if you want to know preciseness, and let's say, for example, how many liters of carbon dioxide gas are going to be produced for every gallon of gasoline that is burned, we need to know quantitative measures. And so that's where we're going with this. We're going to have specific numbers tell us specific things. So I want you to think about sugar and think about it in a canister. How would you measure that sugar? Now, that's a very open question because there's so many different interpretations on how you could measure the sugar. You could either find its mass, very easy, put it on a scale, see how much mass it has. Another way would be to measure its volume. So how much space is it taking up? And then the third way could be that, and this is one that would take forever, is that you could count every individual grain of sugar. That would take you years to do and a lot of patience. So 3 different ways that you can actually find and calculate matter. So sugar was our example, but we can do this for all different types of matter. We can find the mass, find the volume, or find the number of particles. The last one being probably the most difficult, but actually we are going to learn a way that's a lot easier on finding the number of particles than just actually individually counting. And actually, if you tried to count atoms, that would be impossible with what we have right now. All right, so remember back to when I talked about dimensional analysis, we use conversion factors, and these are used to relate the amount of something to its mass. So let's take it back for a quick second. I want you to think of a dozen. And it doesn't matter what a dozen of, but you know that a dozen represents the number 12. Just like if I were to say couple, you would know that that number represents 2. So if I wanted to know how many bananas there are in 8 dozen, I could use a conversion factor to solve that. So again, 1 dozen equals 12 bananas. And if I had 8 dozen, I could do the conversion factor. And I'm not going to do conversion factors, actually, I'll show you what I mean. So basic recall if you don't remember. So remember, if I told you I had, that's an ugly color. I can't really see that very well. I don't know how to change. Here we go. So if I have 8 dozen bananas, that's what I'm starting with. Why is this like this? 8 dozen bananas. That's what I'm starting with. And I want to know how many bananas make up 8 dozen. So then I would use my conversion factor. So it'd be 8 over 1 times 12 bananas over 1 dozen. Does this all look familiar to you guys? You're probably like, oh my God, I thought we were done with this. And then these 2 cross out. You're left with 8 times 12. That should give you 96 bananas. And yes, you were probably thinking, yes, that's super obvious. But in order to do the conversion factors, remember, you have to cancel out your units. We will be practicing conversion factors and dimensional analysis in class just to brush you up on that. So don't worry if that's been such a long time and you're like, I don't remember any of that. All right, so why is dimensional analysis relevant and why is it even something we need to do? So in the world of chemistry, we are dealing with atoms and they are super, super tiny. So molecules and atoms are extremely small. So trying to just count those individual atoms and molecules is not only super unwise, but it's also incredibly impossible. Because if you really try to count in one drop of water, it contains about 10 to the 22nd molecules of water. So that's a lot of freaking water molecules to count. So it would take you about 50 years without stopping to try and count just in that one drop of water. So we need to come up with a better way to figure out how much of something is in something, if that makes sense. So you can thank a guy by the name of Amedeo Avogadro. And what he did was he was responsible for the counting unit of measure called the mole. And so a mole is the amount of a substance that contains 6.022 times 10 to the 23rd representative particles of that substance. So the mole is the SI unit for the amount of a substance. So just like a dozen, a dozen means 12 and a couple means 2, it is a name that stands for a number. So the mole, anytime you think of the mole, you should always think of 6.02 times 10 to the 23rd. So there are therefore 6.02 times 10 to the 23rd water molecules in a mole of water. So if I say I have a mole of bananas, that means I have 6.02 times 10 to the 23rd bananas, which is a lot of freaking bananas. Like I said, anytime you hear the word mole, you should automatically think 6.02 times 10 to the 23rd. So if I have a mole of carbon, I have 6.02 times 10 to the 23rd atoms of carbon. So I don't want you to get these two things confused. A mole, remember, is the amount of a substance that contains 6.02 times 10 to the 23rd. So the name stands for the number. So a mole of something means that you have 6.02 times 10 to the 23rd. I know I keep saying it. So that number is what's known as Avogadro's number, the number of representative particles in a mole. And so what I mean by representative particle is that means it's the smallest unit in which a substance naturally exists. Remember, we've been talking about elements, and some elements naturally exist in nature as just an atom by itself, and it's just fine. Not all elements do. A lot of elements like to combine to be stable or happy, and we've learned about these happies. Remember, diatomic molecules are molecules that will combine with each other in nature and be very much happy like that. So N2, H2, F2, these types of atoms will bond to one another. So the representative particle for these elements is the molecule. And a lot of atoms will bond and make molecules or ionic bonds. So for ionic compounds like NaCl, the representative particle is the formula unit. So a mole of any substance contains Avogadro's number of representative particles. So let's say that I had 10 atoms of carbon and I wanted to know how many moles of carbon I have. So the question would be, how many moles of carbon atoms are in a sample containing 10 atoms of carbon? So I want to go from atoms to moles. And how I do this is by using Avogadro's number. So again, like I said, I have 10 atoms of carbon. So 10 atoms of carbon. I don't have much room to write here. And I want to know how many moles that is. So I would take the 10 atoms. I'm writing it again down here so I have room. I would multiply that by 1 mole of carbon because that's what I want to end with. And then I divide that by Avogadro's number, which is that 6.02 times 10 to the 23rd. And that's the conversion factor. So that's really why the mole is really important or why Avogadro's number is super important, because it's a conversion factor that helps you go from numbers of atoms to moles. And when you go to moles, you can calculate grams. Because in the lab, when I ask you to calculate 10 atoms of carbon, I don't expect you to count the 10 individual atoms. You can't do that. But if you convert that to a more reasonable amount, you can then take those moles and calculate the molar mass, which we're going to talk about here in a second. So if I did the math on that, I would get 1.66 times 10 to the negative 23rd. Now, that's not a realistic number for carbon because typically in any type of sample for anything, I have millions and billions of atoms. For something, I just use 10 to kind of make it a little bit more simple. And I'm going to do so many examples of these in class because I think that the concept of the mole and Avogadro's number can be very confusing and very misleading if we take it too fast. So I've tried to slow things down, but I don't want us to get to a point where we're going way too slow that you're forgetting everything. But all of these, everything we're doing right now is just a conversion factor. So we know how many atoms or the smallest particle that something stays in nature looks like on a more reasonable scale. So like I said, Avogadro's number is a way for us to convert from individual atoms to moles. And this is important because this helps us look at an actual amount. So a unit of quantity that we can easily measure, such as mass. So we need to go from numbers of atoms to numbers of moles to mass. So how we can do this is by using the periodic table to help us, because we know that the periodic table provides atomic masses for us. If you were to look at the periodic table, it provides to you an atomic mass, and I think I've already said this, but I just paused it and I can't really remember. And so using that atomic mass will help you go from moles of something, because if I were to say, oh, I have 20 moles of carbon, you would not know what that looks like. But if we took those 20 moles and used the molar mass of carbon, we could figure out what that looks like in grams. So molar mass is defined as the mass of 1 mole of representative particles of a substance. So basically, in its natural state, it would be 1 mole of carbon or 1 mole of whatever substance we're looking at. So 1 mole of water, but we're using the molar mass. And so the mass of, like I already said that, and how we can, or the unit for our molar mass is known as grams per mole. And this is going to help with our conversion factor because we want to get to grams, we need to cancel out the moles. So like I said, I have 20 moles. I got to figure out how to erase this. Here we go. I have 20 moles of carbon, and I figured this out, remember, using Avogadro's number. So I have 20 moles of carbon. I want to know how many grams that is. So I want to make this like a more relevant term. So I would go to the periodic table and look at the atomic mass. The atomic mass of carbon is 12.01. So 12.01 grams per 1 mole of carbon. So grams per mole. I want to end in grams, remember? So then I would just cancel the moles of carbon, and that leaves me at 20 times 12, which would mean I'd have 240 grams of carbon that I'm looking at. And I know that I'm making this more simplistic. In class, we will do a little bit more of an advanced type of conversion. But I want you to be aware that we are doing a lot of dimensional analysis, a lot of converting from one unit to another using Avogadro's number and using the mole. And we don't just find the molar mass of just plain atoms. We typically do these for molecules. So let's say I had CO2. If you wanted to find the molar mass of CO2, you would have to do a few things of math. So you would take the molar mass of carbon and then the molar mass of the O2, which there are 2 O's, so you would just multiply that twice, and you would get something along the lines of 44.01, and then that would help you convert further. Again, we are going to do all of this in class because I feel like at the end of all these videos, you're more confused than where you started. I highly recommend, if you're not doing too well in the class, that you look at the readings and you catch up or highlight things that you don't understand. I'm finding that you're watching the videos and you're not really listening all that well. So you come to class and you say you have no idea what's going on when you really haven't put forth all of the effort that you could be putting forth. So I definitely think that you need to look into the readings, read those up. If it still doesn't make sense, ask those specific questions rather than saying, I don't get any of this, because that's not going to help you at all. It's trying to figure out where the issues are and what particular portion that'll really help you get farther. If you have any questions, please make sure to ask me on Edpuzzle.